We just finished sample problem 20.6, and in doing that, we kind of looked at the idea that for some reactions where we don't have entropy and enthalpy being favorable, that is, there's a combination of the win-lose situation, we have a temperature dependence of the reaction. And we introduced this concept of a pivot point, meaning that there's going to be a certain critical temperature where the free energy changes from positive to negative. And it has to do with the temperature dependence of entropy. And to kind of illustrate this point, I want to show you a figure that's from your textbook. And so this figure actually looks at the relationship between temperature, the T delta S term, and then enthalpy. So what we can see here, enthalpy is represented by this black line. And we can see that this line is pretty much flat, which kind of reminds us that there's very little temperature dependence on enthalpy. So enthalpy is fairly temperature independent. That is, as we increase temperature, okay, we really don't see much of a change in this black line. However, we do have, obviously, a temperature dependence on entropy because entropy is multiplied by temperature in our Gibbs standard free energy equation. And so what we see in this process, and in this process we can see here, we've kind of labeled this crossover point here. This is what we were referring to as our pivot point before. We can see here that below a certain temperature, we have a reaction, and they show the red here. This reaction is non-spontaneous because delta G is greater than 0. Well, for delta G to be greater than 0, and remember, when we have a temperature dependence, we're going to have one of our thermodynamic components be helping and one hurting. So in this case, when we're at low temperatures and delta G is greater than 0, again, that must mean this term is positive, we're going to have a situation here where we had entropy or enthalpy here that was positive, and our entropy was also positive. Remember, positive entropy is helping, but our temperature wasn't high enough such that we could have this term be larger than our enthalpy term, such that mathematically this negative component would allow us to have a negative delta G. So what we can see here is this temperature is very low, and this T is a very small number. Remember, this T is in Kelvin, and so it's always going to be a positive value. It can get close to 0, so it can go from 0 up to very high values in Kelvin. But when we have a very small number here, this contribution becomes small. And when this contribution is small and we have an enthalpy that is unfavorable, we have an endothermic reaction, the sum of these two ends up being a very overwhelmingly positive value. And so we have a situation here where delta G is very positive, and we have a very non-spontaneous reaction. However, as we start increasing the temperature, what starts happening is we add more weight to our favorable entropy term. And so we can see this T delta S term is becoming larger. It's increasing. And as we do that, the gap decreases here between the magnitude of our T delta S term, which is helping, and the magnitude of our delta H term, which is not helping. And we'll get to a point where they're equal to one another. When these two terms are equal to one another, delta G is 0, and we've defined that as our pivot point. Now what happens if we continue to increase temperature? Again, this calls it a crossover temperature. As we continue to increase temperature, now the magnitude of the T delta S term is greater than our delta H term. And in that case, we have a shift here such that delta G will continue to become more and more negative, meaning our reaction is more and more spontaneous. So I wanted to introduce this concept of a pivot point with this figure, which I think does a really nice job of illustrating that. And we're going to kind of apply it qualitatively then to thinking about this problem. So this problem looks at this chemical reaction, 2SO2 plus O2 creating 2SO3 gas. And they tell us several of the thermodynamic parameters here. They tell us delta G is minus 141.6, delta H is minus 198.4, and delta S is minus 187.9. So this problem first asks us to use this data to decide if the reaction is spontaneous at 25 degrees C. Well, all we need to do to think about spontaneity is look at delta G. And since delta G is negative here, we know that this reaction is spontaneous at this temperature. However, we don't know, just looking at the delta G value, how temperature will affect this. What we need to do to see about the effect of temperature is we need to look at the entropy and enthalpy terms. So if we look at the enthalpy term here, we can see that enthalpy is negative, meaning that this reaction is exothermic, and exothermic reactions are favorable. So this again is our win. What we can see here is entropy here is negative. Entropy being negative is unfavorable. So this is, again, a lose situation. So when we have one of these win-lose combinations, we will have a temperature dependence. That's when we see these pivot points. If it was a win-win situation, that reaction is favorable at all temperatures. We don't have that situation here. In this case, we have to think about whether delta G will change with increasing or decreasing temperature. And this question asks, predict how delta G will change with increasing T. So again, if we apply this here and we say delta G equals delta H minus T delta S, we have a helpful enthalpy term in terms of making delta G negative, and we have an unhelpful entropy term because when we subtract a negative number, we're really adding it. So in this case, because our entropy is unfavorable, we'd like to diminish its contribution, which really means here increasing temperature. Increasing temperature is actually going to decrease the spontaneity of the reaction. We have it being spontaneous at a delta G of 141.6, but as we increase temperature, that delta G is going to become less and less favorable. So we can kind of see that play out here if we solve part B here. So this was kind of qualitatively just thinking about how it would happen. Let's actually do a little bit of calculation crunching and see what happens. And here it says, assuming that delta H and delta S are constant with temperature, that is, there's no phase change occurring, and so we can use these same enthalpy and entropy values and calculate a new delta G at 900 degrees C. It asks us to think about how delta G changes. So we can use the same equation, delta G equals delta H minus T delta S. We're going to put in the same delta H and delta S terms that we had at 25 degrees here. So delta H, again, is minus 198.4 kilojoules. And then we've got 1173 Kelvin. And we're going to convert this 187.9 joules per Kelvin into kilojoules per Kelvin. So it's negative 0.1879 kilojoules per Kelvin. Kelvin are going to cancel. Again, I'm adding a positive term here because of those two negatives. So my delta G ends up being positive 22.0 kilojoules. So again, this is no longer spontaneous. So at room temperature, it's actually quite spontaneous. Heated up to 900 degrees, and it's fairly not spontaneous. So somewhere in between 25 degrees and 900 degrees, we reached our pivot point. And as we'll solve in our next problem when we do sample problem 20.8, we'll talk about exactly how you do that. But I wanted to close with this problem by just kind of revisiting this figure that I showed you. So the figure that we showed you, it was actually the win-lose situation where both enthalpy and entropy were positive. Our situation here is where both entropy and enthalpy are negative. And so if we want to think about how that looks in terms of this figure, and you're not going to be able to read it very well because I actually had to flip the figure this way. I had to actually take it and flip it over. But I'll show you what it looks like. And again, you're not going to be able to read it because all the letters are backwards. But again, when we have a situation, and in this case, delta G equals delta H minus T delta S, now we have our enthalpy being helpful, our entropy not being helpful. So in this case, we have a situation where we want to diminish the contribution of entropy. So we're going to have spontaneity here at low temperature. It's going to be non-spontaneous at high temperature. So in this case, we want to diminish the contribution of our T delta S term. So our T delta S term is going to be significantly reduced if we have low temperature, and so we're not going to be having that contribute in an unfavorable sense to our free energy. So again, just looking at comparing these two figures, but a great figure to remind us that we have changes in free energy about a certain, again, your book calls it a crossover temperature, I've called it a pivot point, and we have those situations where we have our win-lose combinations.